量子力学と人間の自由意志。
I don't think there's any difference. I mean, the time that physicists deal with is essentially the same as ordinary time, except that physicists think of microseconds or picoseconds instead of just seconds. That means millionths of a second or trillionths of a second. So physicists can think of very short intervals of time, but that doesn't really make much difference to ordinary life. I think much more big changes in our thinking are coming along with biology rather than with physics. When biology advances, then we think differently about ourselves. And that really does make a difference. I mean, for example, at the moment, the most rapid movement in biology is neurology. We're learning how to study our brains and to take moving pictures of brains with magnetic fields. So you can actually see things going on in our own heads when we're thinking. And that's going to change the way we think about ourselves, I think, in a much more fundamental way. Well, I can't say I'd talk about it in depth, but it's true that quantum mechanics makes atoms unpredictable. I mean, that was the big surprise, that when you understand atoms, it turns out you absolutely cannot predict what they're going to do. That the laws are just don't allow exact predictions. There's a certain kind of freedom that atoms have to jump around, and they seem to choose entirely on their own without any input from the outside. So in a certain sense, atoms have free will. So that's, to my mind at least, it's probably connected with the fact that we have free will. We have at least a strong feeling when we decide to move a hand up and down that we're free to do it or not. And so it could be that we are actually using the freedom that quantum mechanics allows. So the brain is a kind of an amplifier which takes the freedom of movement of atoms and translates it into freedom of movement of our whole body. So that's at least my feeling about it. And we don't understand it in detail, but it looks as though there is a connection. Well, the human mind is just a sort of a clever device for using this freedom in order to achieve some kind of a purpose. And of course, animals in general do that. And humans have reached the point of being aware of what they're doing.
20世紀初頭から始まった量子力学は、実に重要な検証実験を経て現在に至る。その検証実験で、今までの物質的世界観とは相入れない事実が明らかになった。そのため、多くの物理学者が、意識や人間の自由意志に肯定的である。それは、量子力学が、微細領域の物理運動というスケールの問題を超えて、量子力学が非局所性を持ち、波動関数の重ね合わせ状態が人間の観測によって収縮する、あるいは観測器の有無によってスリット通過後のスクリーン到達パターンが違うという実験結果は従来の物理学との大きな相違を見せつけた。それにより、オイゲン・ウィグナーやジョン・ホイーラーたちは自然の成立には人間の意識も関与していると提唱した。しかし、唯物思想を頑なに信仰する連中は、人間の意識や自由意志は 錯覚だの幻想だのと言って唯物的自然観を維持しようと必死だ。今後、新たな自然観が要請される検証実験が提案されて、唯物論者は大恥を覚える。量子力学創設者の一人であるマックス・プランクは、次のように言った。人間の最大の謎として、人間個々人の意志の独立が、人間が自然法則の厳格な秩序に従う、宇宙の不可分の部分であるという事実とどう調和しうるのか。しかし、その謎は徐々に解明されつつある。人間が最初に取り組んだのは、人間にとっては、客観世界である自然の運動法則を探すことであり、それは自然界の近接決定作用として働くことが分かった。しかし、1877年にルートヴィヒ・ボルツマンが、物理系のエネルギー準位が離散的とする仮説を出し、1900年にマックス・プランクが量子仮説を提唱した。この各公子が離散的にエネルギーを持つという発見は、その後、量子力学として発展し、1925年にベルナー・ハイゼンベルクが不確定性原理を発表した。1935年、アインシュタイン、ポドルスキー、ローゼンらが EPR パラドックスの論文を提出。ニールス・ボーアはそれに反論。この EPR 相関の問題が発表された当時、アインシュタインらは局所実在論の立場をとっていたため、ある物理量が実在すると言える条件は、その物理量を有する形を乱すことなしに、その物理量を確実に予言できることとした。量子論は、位置と運動量のような2つの物理量測定の場合には、一方の物理量測定値を得るには、もう一方の測定値が不明になる。アインシュタインらは、このことを挙げて、量子論は不完全だと論じた。ジョン・ S ・ベルは、セルンの研究者として活動中、1964年に発生源を同じとする2つの粒子を遠距離に離して、その片方のスピン重ね合わせ状態を確定させると、もう片方のスピン状態もそれに対応して瞬時に確定するという量子論から導き出される作用を応用した仮想実験を考案した。それは古典物理の局所実在を前提として実験して、その場合は不等式の枠内に入り、量子論に従う場合は不等式を破るという巧妙な不等式を提出したオランダ、デルスト大学ロナルド・ハンソン氏と研究チーム。それは、局所実在論が正しいなら満たすべき相関の上限を与える式である。その後1980年代の初期に、フランスのアラン・アスペは、ベルの不等式を検証する実験を行った。その実験で、アスペは、ベルの不等式が破られていることを示したが、この実験には、不完全な点があるとして、完全な検証を求める学者もいた。重要。この世界は、確たる決定論の法則で運動しているわけではない。2015年10月21日、オランダのデルスト大学ロナルド・ハンソン氏の研究チームは、厳格な要件を満たしたベルテストを実施と発表。画期的な結果は、2015年10月21日にネイチャー誌に掲載された。量子的相関の議論では、離れた距離での電子との間の相互作用は以前に実証されているが、これらの実験では、電子が瞬時に他の原因で応答する可能性が依然として存在した。今回実験を行ったデルスト大学の研究者は、彼らの実験で、このベルテストの厳格な要件を満たした。独創的な方法のこの実験は、相関する電子対の両方の粒子を測定し、可能性のあるすべての抜け穴を閉じる。今まで、これらの実験は、いずれも決定的観測のローカル因果説明を除外しなかった。しかし、今回の実験は抜け穴がない。オランダで行われたこの実験では、技術的に非常に厳しかったローカル因果関係を排除することに成功した。これは、 最終的には、因果的影響のいずれかが、光よりも早く伝播する。さらに、客観的実在は、一つだけの確たる実在、破存在せず、あるいは原因を意味するものについての、常識的な考え方が間違っていることを証明する。それにより、自然界において局所実在性が成り立たないことが示された。20世紀初頭から始まった量子力学は、このような検証実験を経て成立している。
I'm Roger Penrose. I'm the Emeritus Rousball Professor of Mathematics at the University of Oxford. I've been interested in issues to do with consciousness and its connection with deep issues in physics for many years. I certainly hope that this conference will be an opportunity to convey ideas of deep importance in how science is trying to grapple with these questions of consciousness and to promote these ideas to the general public and the arguments that go on between different points of view, which will go on and which must go on for a long time to come. There is a current view that consciousness is something which arises from some complicated computation. So we have our computers, and people think that because they can do things amazingly fast and they can calculate very quickly and they can play chess extremely well, that they're superior to us even, and that it's only that some complicated aspect of this computational activity, somehow consciousness arises from that. Now my view is quite different from this. I think there is a lot of computational activity going on in the brain, but this is basically unconscious. So consciousness seems to me to be something quite different. What we do when we understand something is not computing. There's something else going on. But at the same time, I'm a great believer in science, and that what's going on in our heads is still obeying the same laws that are going on in the universe outside us. However, those laws are not things that we necessarily fully understand today. To be understanding something, you need to be aware of it. And to be aware of it, you're conscious of it. And so you are invoking your consciousness. So to me, there is something outside the computational laws of physics. And when I wrote my book, The Emperor's New Mind, I was trying to develop this idea, and I was trying to say, well, there is something else out there. What could it be? Where is the biggest gap in our understanding of physics? There are lots of gaps in, we don't know what governs the masses of particles. We don't know all sorts of detailed things. But most of these things don't have a direct bearing on what a brain does. I mean, it's the wrong scale. There is a big gap in our understanding of the laws, and this big gap is within present-day quantum mechanics. There are two procedures in quantum mechanics, the Schrödinger equation and the making of the measurement, and they're inconsistent. I say it quite strongly. It's not just that we haven't got the right interpretation of quantum mechanics, they're just inconsistent. Now that's interesting. If there was a huge gap, maybe that gap is where the theory has to be outside a computational system. Okay, this is, many people will dispute that and they say, well, this is, taking your logic too far and so on. Well, it seems to me there is logic in this. The next step, though, is the one that people mostly question. Because if inside our heads we are exploiting that gap, it means that we have quantum development in the system which takes us to a level somewhat beyond present technology in our experiments. The experiments still support quantum mechanics, and we have not yet seen where something new has to come in. But there are good reasons, in my opinion, when we look at going back to these two major revolutions of 20th century physics, quantum mechanics on the one hand, Einstein's theory of general relativity, space-time is not flat, it's curved, gravity is not a force, it's somehow a curvature. There is something quite different from other kinds of physics going on there. If you bring these two great theories together, we see this conflict suggests strongly that there must be a change in the rules of quantum mechanics at a certain level. And that certain level is not too unreasonable that it should be relevant in the brain, because it has to do with the movement of mass of a very tiny amount. It's very big for quantum mechanical experiments, but very tiny for even for things in biology. So we're looking for tiny displacements of mass. That's the Schrodinger's cat, if you like. They can be in two places at the same time, but then it spontaneously becomes one or the other. And in its becoming one or the other, it's doing something non-computational. Now, when I wrote The Emperor's New Mind, I knew something about nerve propagation, and it just didn't seem to me there's a chance. There's no chance, because in nerve propagation, it disturbs the rest of the brain in a way which would completely destroy the coherence that you would need in your quantum system to be able to probe this new level in quantum mechanics. But still, I thought, when I finish writing the book, maybe I will see the answer. No, I didn't. But the answer, in a certain sense, may have come because Stuart Hameroff read my book, and he contacted me and said, well, look, maybe you don't know about these things in the brain, these microtubules. And I thought, microtubules, what's that? In my ignorance, I didn't know about them. If I had, I might have said, well, maybe that's a good place to look. And it seemed to me that was a much better place to look. You could conceivably imagine the kind of isolation that was necessary. It still goes beyond normal people's understanding of the kind of isolation you would expect to find in a cell, but there is a reasonable chance. And since it happens, since we are conscious, we can understand things, we seem to do things which go beyond a purely computational activity, the logic is, well, maybe this is in the microtubules, because that's the best candidate I've ever seen. And so we got together, and the ideas we then developed from there. My ideas came from the physics and from my desire, the feeling that in order to understand consciousness, we need this kind of level of coherent quantum mechanics, and that the state reduction has to come in. So it's the idea of the OR, if you like, has to be part of the scheme. But then exactly why, what part of the brain's involved, and where, what is the neurochemistry, what are the structures in the brain, that's all Stuart. So mine is on the physics side, and his is on the biological side.